Welcome back friends. We will continue our discussion from the earlier class of the week. In the earlier class we started discussing about the water quality aspects, and we did talk about what are the various sources of the pollutant in the water and why it is important to remove the pollutants from the water before it is sent to the end consumers, what kind of effect these can lead in terms of the chronic or acute effects on the end consumers, and how the consumer may get exposed to these pollutants. Now in this class we will be focusing on the assessment of water quality and how we can basically say certain water is of good quality or bad quality using the water quality parameters. So practically we will be discussing about the different water quality parameters in this week. Now these are the same images which were displayed in the earlier class as well. So we see that there are two sources of water here. Okay. In the earlier class we said that the two sources of water here kind of give an idea that the quality of water is different in these two sources. That is okay, the quality of water may be different, but which one has better quality and which one has poor quality. So apparently, like just by seeing one will say that this water looks more dirty or more turbid, okay, but is that enough to suggest that this is of bad quality water than this? Okay. Who knows that this may have certain contaminants which are far more toxic than this water, because this apparently what we are able to see is the sediments, the turbidity and the filterable material which may be very rather like easily removed, whereas this may have certain contaminants, say may have some pesticides or antibiotics or some other kind of contaminants which will not impart any color, taste or odor, but may be far more dangerous than the contaminants present in these water. So the point here is only physical appearance may not be sufficient to distinguish the quality of water. Just by appearance, if a source is looking very clean, that does not mean that water quality is good in that source. It may be good, but it may have certain contaminants which is undesirable in a sense that it may be toxic, it may be unwarranted, it may be like harmful to the consumers, but it is apparently not giving any color, taste or odor or any physical, it is not changing any physical attribute of the water. So the contaminants which does not change any physical attribute of the water is hard to detect just by physical appearance, because it is not changing anything in the water which can be physically detected. So if the nature of the contaminant is such, it is not possible to detect that contaminant just by observing the water. In any case, even if you say like this is this is practically looking a water which is having lot of contaminants or turbidity or floating materials, okay, but how we say that what is the quality of this source, how we signify that? Just by seeing we can say okay, the water look dirty, but dirty means what? Okay, dirty is just a kind of qualitative assessment. We can say that okay, it is dirtier as opposed to this one, okay, but what is the characteristic of this water? So because we cannot distinguish just by the physical appearance, we have to go for the assessment of water quality through certain parameters, and these parameters are called water quality parameters, which typically show the physical, chemical and biological properties of the water. So the characterization of water is typically done in terms of these water quality parameters, which eventually will show that what is the value of these parameters in the water, and which will help in quantitatively estimate the characteristic of water, not just qualitatively, not just good, better, bad or does not look good kind of observations, but to be precisely, if we say that this water is contaminated, we can quantitatively tell what is the level of contamination in this water. Say for example, if we are saying this water is colored, so what is the relative value of the color? If this water is turbid, what is the value of the turbidity? If this water has solids or suspended solids, what is the amount of the suspended solids present in the water? Okay. So, similarly, so there are different set of parameters, physical, chemical and biological properties are assessed through these parameters. There is no specified list of water quality parameters. Okay. We may have n number of parameters, there are several parameters. The parameters essentially test the quality of water or the level of pollutants present in the water. Now, there are more than 80,000 chemicals registered and all of them somehow or other way may enter the water, at least majority of them may be present in the water at some place or some stages. So, they might be detected. So, that the detection of one chemical may become actually a one parameter. So, there is no specified list of water quality parameters, but there are certain common water quality parameters which are more popular or which are more frequently used. So, these parameters include likes of the temperature, color, odor, turbidity, conductivity or electrical conductivity, then solids, different type of solids, then various chemical parameters like pH, acidity, alkalinity, hardness, nutrients, metals, ions, pesticides, radioactive emissions, dissolved oxygens, BOD, COD and various other trace elements. Okay, some biological parameters like most probable number, total and fecal coliform. So, these are some of the parameters which are estimated for getting an idea of what is the level of the contamination present in the water. So, the parameters that we listed, so we will be discussing some of these parameters which are more important. So, like pH is generally well known to everyone, it is minus log 10 of the hydrogen ion concentration, and this is measured typically through pH meter, which consists of voltmeter which is attached to a pH responsive electrode and the reference electrode. So, pH of fresh water is typically in the range of 7. So, pH of water is in the range of 7, and if we move below 7 we get the acidic characteristic, and if you go higher than the 7 we actually face the basic characteristic. Water up to pH 6.5 to 8 range might also be considered okay. However, it may vary in some cases like from 4.5 even to over 10 in certain cases. The pH of water may vary depending on the source of water. If some pH water is basically flowing through the limestone region and there is things, so it acquires lot of alkalinity and its pH becomes high. Similarly, if water is flowing through the or kind of acid mine drainage or those things coming in, they may have a low pH, okay, even lower to 4.5 is also a possibility. So, that way the pH kind of decides what is the acidity or alkalinity in the water. It is not that just pH decides that, but it gives a basic idea whether the characteristic of the water is acidic or alkaline. Then the temperature, which basically governs the form of the constituents or pollutants present in the water. Okay. There are many constituents which are if the temperature of water rises below certain limit, they may get evaporated, okay, or there are certain biochemical reactions which are controlled by the temperature. So, the rate of the biochemical reactions may also be controlled by these by the basically prevailing temperature of the water. The temperature of water is typically measured using thermometers and it can be reported as degree Celsius, degree Fahrenheit or degree Kelvin. Then the conductivity or electrical conductivity is a parameter which basically talks about the ability of water to carry an electric current. Now, pure water is a very poor conductor of the electricity. Pure water cannot conduct electricity. Okay. So, the water, if it is showing significant conductivity, that means it is having some dissolved salts, because water has to have ions in order to carry the charge. Okay. So, the salts when dissolved in the water, they get ionized and these ions are able to carry the charge. So, if there are substantial conductivity or significant conductivity in the water, that means there are presence of the dissolved salts which are able to carry the electricity. So, generally over most ranges or particularly the lower, the conductivity is directly proportional to the amount of salts dissolved in the water. Okay. The conductivity is typically measured using a conductivity sensors, which in 1 centimeter cells it says that basically how the current is passed through the water. So, what is the resistance or conductance it is offering, and is typically reported in Siemens per meter or Siemens per centimeter. Okay, it may be in a micro Siemens as well or millisiemens as well in time. So, if you see, the conductivity of ultra pure water is very low, of the order of 55 nanosiemens per centimeter. Okay. Then pure water will have conductivity less than 1 microsiemens per centimeter. The processed water typically has 10 microsiemens per centimeter. Drinking water may have conductivity of the order of 100 microsiemens per centimeter, because we do not drink distilled water, we do not drink pure or ultra pure water. Okay. We want to drink water which has certain minerals in it. So, the drinking water may have, and in fact should have, certain conductivity, it should not be completely devoid of the conductivity. Okay. And then there are basically the milk have a conductivity in the range of 1 millisiemens, and juices in a higher range, then the acids and these things, the conductivity is even more higher. So, that way we can actually have an idea of the characteristic of the water by measuring the conductivity. And as conductivity, as we said, that is generally proportional to the level of dissolved salts present in the water. So, conductivity is taken as an indirect measurement for various other parameters, which includes the total dissolved solids, because it is proportional to the dissolved salts. So, we can have an indirect assessment of total dissolved solids using conductivity or salinity. Okay. So, salinity can also be measured using conductivity, because that is also a form of the dissolved salts. So, the salinity or TDS also can be measured through the electrical conductivity. Okay. Or generally the conductivity meter that we have, the conductivity probes, in the other mode they will be able to give the direct value of TDS or salinity. Then the color and order are other couple of parameters which are important more from the standpoint of aesthetics. Okay. Both are objectionable in the water, okay. Particularly for drinking purpose. So, no one wants to have a color or order coming from the drinking water. People avoid using color water, even it is safe from the public health aspect. Okay. So, color is generally caused by the organic substances such as algae or humic compounds. The color typically could be of two types. So, one is called true color, which is caused by the dissolved or colloidal solids present in the water. So, if you take a dye, pinch of dye and put it in the water, it gets colored. Like now, you keep that water for a day, couple of days, 7 days, a week, or even a higher time, you will not see that the color of water is changing, it is still colored water, okay, because it is due to the compounds which are already dissolved in the water, or for in some cases even in the colloidal stages, because colloidals also are not typically removed just by statically holding the water. However, there are other type of color which are called apparent color, which is primarily because of suspended solids or suspended matters. So, it is actually the color, not color of water, but color of the suspended matters, and as the suspended matters settle down, the color of water will get removed. Okay. So, these kind of color are called apparent color, because it is not the true color of water, it is just apparently visible because the suspended matters is there, which is colored. So, once the suspended matters filters out or once suspended matter settles or filtered out, you will see the water coming is actually colorless. So, these two types of color are there. For measurement purpose, color is measured on the standard color unit, and the standard color unit is made by dissolving 1 milligram per liter of platinum and 0.5 milligram per liter of cobalt. So, if we dissolved this if we make a solution which is having, say, we take 1 milligram of the platinum and 0.5 milligram of the cobalt and dissolve these two in 1 liter of water, the color of that is considered as 1 unit of color. And then through sequential dilution, if we have a water, colored water, and we want to measure the color in that, so let us say this is our sample, so we dilute this sample say 100 times. So, we have a 100x dilution and then match its color with the standard unit, we see still darker, we again dilute it 10 times, then we match, we see still darker, we again dilute it say 5 times, we see that it is now getting close, but it is still far off. So, we again dilute it say 2 times and then we see that okay, now this is more or less matching with this. So, the unit of the color in standard unit is because we had a 100x dilution, then 10x dilution, then 5x dilution, then 2x dilution. So, you have to multiply all these. So, 5 into 2, 10 into 10, 100 into 100, 10,000. So, the color is actually 10,000 units, standard units of color. So, that way we can determine the color. That is a old traditional method. Nowadays, the spectrophotometric determination of color is also getting more popular in fact, okay, where the color is determined through spectrophotometer and it is represented at some specific wavelength, select wavelength. So, we can have absorbance value as say lambda 400 nanometer. So, at lambda 400 nanometer, what is the value of color? What is the value of absorbance at lambda 400 nanometer, or we can have say absorbance at lambda 400 nanometer and this represents the color at 400 nanometer. The order in water is also objectionable. The pure water is again orderless, but it may acquire order through substances which are dissolved. Generally, decayed organic substances give falling smell, whereas inorganic substances may give earthy smell. Okay. And order also be measured through threshold order test, okay, where the dilution factor is determined to make the water orderless. So, again it is a kind of similar approach. Okay. So, we have let us say a sample which is say V volume of sample, okay, or VA volume of sample, and then we add this is having certain order. So, we want to add, we will keep on adding water, pure water, orderless water in this until unless it becomes orderless. So, let us say we required VW volume of pure water in order to make this orderless. So, the total volume becomes VA plus volume of water that is needed to remove any order. So, VW VA plus VW, and then we divide it with the volume of sample which is again VA. So, this gives us the threshold order number. Okay. So, this is what is used for determining the order in the samples. Now, the other parameter is turbidity. Turbidity is again an optical property. It describes the clarity or the haziness of the water. Okay. So, simply like if we pass light through a water, if it is a clear water, light will easily pass through this, but if it is having lot of suspended or colloidal materials, so light will not pass, but when it strikes to those particles it will get scattered. So, the more scattering, that means more turbidity, less scattering, that means less turbidity. So, we can see that basically the waters which look clear will have low turbidity, and water which looks quite dark or dirty will have the high turbidity. So, when we move towards low and high turbidity, we can realize that how the kind of level of clarity is reducing and level of haziness is increasing in the water. Okay. Turbid waters are also unacceptable to consumers, and turbidity may also affect the treatability of water, which we will be discussing later, because when there are suspended materials present, and if for certain cases, let us say if you want to put a UV light disinfectant and those kind of thing. So, this turbidity may stop the path of the light, and the light may not hit the intended target or bacteria or those kind of things. So, that way basically it can create problem in the treatment process as well. Turbidity is measured by basically passing a light beam. Okay. So, a light beam is passed through a monochromator and then it actually goes through the sample. So, then once it goes through the sample, part of light can actually transmit. Okay. So, and if we detect the light which is transmitted, then also we can determine the value of turbidity, and this principle is called turbidimetry, where we basically detect the light which is transmitted through the water, whereas this is no more used. In fact, the popular one, or which is used these days, is the one which detects the scattered light and not the transmitted light. So, same principle is followed, and the detector is placed at the right angle of the sample. So, the light scattered at the 90° or right angle is measured and detected, and then we get the value of turbidity. So, this principle is called nephelometry. So, nephelometry is the one which is used for measuring turbidity these days, and as a result the unit of turbidity is NTU, which is nephelometric turbidity unit. So, turbidity is represented in terms of NTU, which stands for nephelometric turbidity unit. So, this is about turbidity. The next important parameter are acidity and alkalinity. Okay. Now, acidity and alkalinity of water indicates the capacity to react with the acids or bases. Okay. So, acidity will be basically its capacity to react with the base, and alkalinity will be its capacity to react with the acids. The concept is basically, concept of acidity is opposite of the alkalinity, however both are based on the carbonate systems. So, in water we have basically we may have molecules in the different forms. So, we may have H ion, OH ion forming H2O. We may have H2CO3 plus OH, which is forming HCO3, HCO3 and OH forming carbonate. So, we may have different form of carbonates present in the water. Okay. Now, where the carbonate molecules, which is H2CO3, HCO3 and sometime even the H ion attributes to the acidity, while the carbonate means CO3 minus 2 and bicarbonate HCO3 minus or hydroxides contain this attributes alkalinity. So, that means if water is having the H2CO3, HCO3 minus and H plus in the predominant form, you will see that it is more acidic, whereas if the carbonate, bicarbonate or hydroxides are in the dominant form, so then we will see that it is more of the alkaline water. The alkalinity can exist down to pH 4.5. Generally people say that the water above 7 is alkaline, but that is not totally true, because if we end up determining the alkalinity, so alkalinity can be as low as pH 4.5, because HCO3 minus can not be completely neutralized before this pH. So, the total alkalinity will be HCO3 plus twice of the carbonate available plus OH minus H ion. This is what gives us the total alkalinity. The acidity in the water is determined by the titration through sodium hydroxide solution, whereas the acidity can be determined by titrating a standard acid. Okay, and we can use 4.5 and 8.3 as a indicator or end points in both the cases. Okay. So, the amount of the base or sodium hydroxide required to neutralize the sample means if the sample pH is below 4.5, so we titrate it to reach to the 4.5, which is basically methyl orange end point. It is measured as the mineral acidity, okay, while the amount of sodium hydroxide to reach the pH 8.3 is known as the total acidity. Similarly, if the pH of the water is higher than 8.3, so we bring it down to the 8.3, which is reported as the phenolphthalein alkalinity and or basically the caustic alkalinity, and then we titrate it to the 4.5 in order to get the total alkalinity. So, for pH, let us say if we are having a water of pH 7.5, that means it is not having any caustic alkalinity, it can only have the total alkalinity when we titrate it and bring it down to 4.5. But if we are having a water of pH 9, so then when we bring it this 9 to 8.3, pH 9 to pH 8.3, this portion reflects to the caustic alkalinity and then when we bring it again back to the pH 4.5. So, the total combined caustic alkalinity and this combined will give us the total alkalinity. Similarly, for samples with pH above 4.5, there is no mineral acidity, but if the pH is less than 4.5, the amount needed to neutralize or to reach till pH 4.5 will give us the mineral acidity, and when we titrate it back to the 8.3, we get the total acidity. Then there are hardness. Hardness is basically caused by the presence of calcium and magnesium ions. If these ions are present as bicarbonates, we call that temporary hardness. If they are present as the sulfate, chloride, nitrates, we call that permanent hardness. So, hardness is commonly measured by the titration with EDTA solution, but there are test strips and other things available, and depending on the value of hardness, there are standards which can be adopted for calling that water as soft. So, like international standard is from 0 to 50, hardness less than 50 milligram per liter as CaCO3 is called soft water, up to 100 it is moderately soft, up to 150 it is slightly hard, 150 to 200 it is moderate hard, and greater than 200 it is hard, greater than 300 it is very hard. Whereas US standards up to 60 they considered soft, 61 to 120 they considered at moderate hard, 121 to 180 they considered hard, and above 180 they considered this water as very hard. Okay. So, that is about the hardness. Then there are solids present in the water. Okay. So, solids actually could be of many types. Okay. The total solids present in the water is the mass of all the form of the solids present in the water. Now, this total solids can be either in the suspended or dissolved state, or could be in the volatile and fixed state by nature. Generally, the measurement is through gravimetric method, means we filter the sample. So, like if you are having a water sample, we filter it with glass fiber filter paper, and then the amount retained on the filter is the total suspended solids, and amount which has passed through filter is the total dissolved solids, and then we put these in the oven, okay, muffle furnace, which is heated at 550 degrees Celsius. So, after filtration we keep it in the oven at 104 or close to 100 degrees Celsius, 100 to 104 degrees Celsius, and this we keep up for about 24 hours, and then after heating we cool it to room temperature and then measure in order to get the total suspended solids and total dissolved solids. Whereas, we keep the sample again in the furnace and heat it for 20 minutes in the furnace, so that all the solids which can vaporize, generally the organic materials, will escape, and whatever is left is the fixed part. So, the amount which has escaped is basically the volatile part. So, if we see the weight difference between here and here, so the difference part is the volatile part because it has escaped the system, whereas what is the residue left over is the fixed part. Similarly, for the dissolved solids also. So, we get the volatile dissolved solids and fixed dissolved solids. Now, we can sum up those suspended parts, and we can get the total fixed solids and total volatile solids, and summing these two we can get the total solids. So, generally the inorganic salts often remain in the dissolved state, okay, and they are non-volatile at temperature. So, they form the fixed dissolved solids and fixed suspended solids. If there are particles like sand, silt, clay, those kind of thing, so they will be as a fixed suspended solids, whereas organic compounds are often volatile at high temperature. So, the organics which are dissolved in the water like sugar, fatty acids constitutes the volatile dissolved solids, while organics which are suspended like microorganisms or suspended organic matter, they will form the volatile suspended solids. So, summation of the fixed dissolved solids and volatile dissolved solids will give us the total dissolved solids, and volatile suspended solids and fixed suspended solids will give us the total suspended solids. So, that way we can determine the different types of solids present in the water. Now, one of the most important water quality parameter is the microbial count, okay, because as when we will be discussing the treatment part, then also we will talk about it. But generally, even if you are not able to provide treatment for any other thing, it is the microorganisms or biological pollutants which gives the acute effect. So, you can nobody wants to drink a water which is contaminated microbially, because that will give an acute effect. So, that has to be removed, and how much, whether the water is microbially contaminated or not, is tested through these tests. So, MPN is one of the most popular or most commonly applied test for that, okay, for testing the microbial quality of the water. The fecal coliform is taken as an indicator for fecal contamination of the water. So, procedure is there is typical procedure given in the American Water Works Association manual or American Public Health Association manual, okay, and that is what is typically followed. So, there would be basically samples taken in a series of test tubes, and then various replicates of the test tubes are prepared. In these test tubes, in fact, there is basically a sample is taken, and we may add nutrient broth or this thing, so that if any contamination, if any microbial contamination is there in the tube, it can actually grow. So, in the tube we again add a small inverted tube which are known as the Durham tubes, okay. So, and then we basically plug this or with the cotton or other thing, and then incubate it for 24 hours, and then after 24 hours we see. So, if this will be basically filled with the solution up to here. So, if the water will be there in the Durham tubes also. Now, if there are microbial contaminants present, so when they will respirate, they will produce the gas, because this is an inverted tube. So, gas cannot escape, and we will see the gas bubble trapping in here. So, the gas bubble trapping in here is considered as a positive test, and if we do not see any gas bubble in the Durham tubes, we consider that as a negative test. So, positive test means there are microbes present, negative test means there are no microbes present. Now, we prepare 3 replicates of the different dilutions, and then we count number of positives. So, for say we get different dilutions means one set we prepare of 3 test tubes as it is, okay, no dilution. Another we prepare with 10 times dilution, this is 10x, this is 1x or no dilution, this is 10x, and then one set we prepare with the again 100 times dilution, which is 100x. So, we monitor number of positive in these 3, and depending on any such, let us say we get 2 positive here, 4 positive here, no positive here, that way, and then correspondingly we can get the MPN number and it is a confidence limit. So, that is how basically we report MPN. MPN stands for most probable number, and it is not mean, it does not mean that if say value of MPN, it is typically reported as numbers per 100 ml. So, say if we report MPN of a water sample as say 20 per 100 ml. This does not mean that there are 20 microorganisms. This means that the probability of having 20 microorganisms is the highest as opposed to probability of having any other number. Remember, the MPN stands for most probable number. It does not state that it is actual measurement of the microorganisms. It is just measurement of the probable number. So, it says that the probability of having 20 is the highest as opposed to any other unit, and this is how it is reported generally. The numbers per 100 ml is the unit for MPN, typically conventional unit for MPN. Then there are metals present in the water, okay. These metals, some metals are actually useful, okay, but even though when they are present in the excess they become toxic, like fluoride is useful to certain extent, but higher concentration of fluoride is toxic, same with the other minerals, various other minerals, but then the higher concentration of these becomes a problem. The metals are typically detected using atomic adsorption spectrophotometer or electrochemical atomic adsorption or inductive coupled plasma equipments, okay. IPC mass spectroscopy is also used, and certain metals like arsenic, cadmium, chromium, lead, mercury, etc., selenium, etc., are classified as priority pollutants as well. Water may have nutrients as well, so which is nitrogen and phosphorus particularly. There are again environmental and health issues of this. Environmental issues of the nutrients are more prominent because they lead to the eutrophication or algal bloom, whereas these due to algal bloom they may impart some toxins into the water, which can be basically a health risk for human as well if we come into the contact of those waters. These are generally present in both organic and inorganic forms, and organic forms of the nutrient may also eventually get converted to the inorganic forms. There are different forms of the nitrogen and phosphorus which are measured. So, we may have a total phosphorus, total dissolved phosphorus or orthophosphates as the form of phosphorus, or total nitrogen or total Zeldal nitrogen, TKN, or nitrate, nitrite and ammonium forms of the nitrogen. Okay. So, there are standard chemical procedures or field laboratory kits are available for measuring these nutrients in the water. Then there are emerging contaminants which include variety of compounds such as pesticides, pharmaceuticals, personal care products, then other antimicrobial or antibiotics, hormones, so the surfactants, a variety of compounds are considered under these. So, these are the non-traditional contaminants which are referred as emerging contaminants. These are generally unregulated at most places, okay, while some countries are coming up with regulation for controlling these emerging contaminants as well, but at many places they are still unregulated. Okay. So, this is a typical list of variety of those contaminants, like for antibiotics, the other pharmaceuticals, this is the steroidal hormones, this is the typical household and industrial chemicals including insecticides, antioxidants, fire retardants, pH, plasticizers, surfactant derivatives. So, these are also a form of contaminants and can be measured. Okay. Lastly, we will talk about couple of parameters which are not that important for water supply perspective, but more important from the wastewater point of view. Okay. These are dissolved oxygens, which is basically refers to the amount of oxygen dissolved in the water. Now, water can both produce as well as consume the oxygen. It can produce by the gain from the atmosphere, so through atmospheric exchange with the layer, and it can also gain from the photosynthesis by the aquatic plants, whereas it can consume oxygen in the process of respiration by the aquatic animals and the various reactions which may consume oxygen. So, the DO levels in water fluctuates, and it not only fluctuates seasonally, but it will fluctuate over 24-hour period as well, because photosynthesis rates are different. So, we get no photosynthesis in the night, highest photosynthesis in the daytime. So, if you go for measurement of the dissolved oxygen in a water body in the afternoon, you are likely to get more DO as opposed to if you go measure the same water body in the night. Okay. Also, it varies with the water temperature and altitude. So, the cold water holds more oxygen than warm water. As the temperature increases, the oxygen kind of is not retained in the water, it will escape to the atmosphere. Similarly, water at basically higher altitudes will hold less oxygen as opposed to the one that are at lower altitudes. So, in deep water bodies, in basically if the water bodies are shallow, there is not much vertical stratification, the oxygen level varies along the basically along the length of the river, but in deep water bodies we may have vertical stratification in DO as well. DO is typically measured through DO meters and probes, whereas traditionally the Winkler method or Azide-Winkler method has been popular method for DO measurement in the labs. Then there are COD and BOD, which are chemical oxygen demand and biological oxygen demand or biochemical oxygen demand. Both are measure of the organic matter in the water, and they do report in terms of oxygen required to oxidize the organic matter. Now, COD reports the oxygen requirement for oxidizing it chemically, whereas BOD reports oxygen requirement for oxidizing it biochemically or biologically. Okay. So, COD is typically measured by incubating water at with a strong chemical oxidant, generally potassium dichromate is used K2Cr2O7, and it is done in an acidic medium. So, there is basically H2SO4 and it is incubated at higher temperature, generally boiling temperature 150 degree is used, whereas BOD is monitored as time wise DO reduction in the microbially seeded water samples. So, we may actually have water samples if it is containing organic carbon, if we seed it with the microorganisms. So, the in the process of decomposition of organic carbon, the DO level will reduce. So, we measure the initial DO level and after certain times. So, generally BOD is measured for after 5 days. So, say after 5 days how much oxygen level has reduced, we report that as a BOD 5. Okay. So, there are other then different forms of BOD also. The BOD requirement for carbonaceous material is CBOD, for nitrogenous material or basically for oxidation of the nitrogen species it is required is called NBOD. So, we may have CBOD and NBOD type, but that is more prevalent to the wastewater system. So, we will not be basically having more discussion on that here, but just to give an idea that these are also important parameters, important water quality parameters, but more important for the wastewater purpose. Okay. As both actually measures the indirect measurement of organic material, okay, but COD measures it chemically with a strong oxidant, so which can almost oxidized all oxidizable elements in the water, whereas BOD measures the approximate amount of organic matter which can be oxidized biologically. So, biologically only biodegradable organic matter can be oxidized. So, BOD is actually an assessment for the biodegradable component of organic matter, whereas COD is an assessment of almost all the organic matter present in the water or all the oxidizable matter present in the water which can be chemically oxidized also. So, that is why the COD values are typically higher than the BOD values, because whatever is microbially oxidizable that can also be chemically oxidized. So, the BOD component is already there in COD. In addition, those which cannot be oxidized biologically, so non-biodegradable compounds which can be oxidized using dichromate are also included in the COD. So, we get higher COD values than the BOD usually. There are another such parameter TOC, total organic carbon, which is well correlated with the COD, because that is also an approximation of the organic carbon. Apart from that, there are other compounds such as various iron, sulfate, nitrate, those things also. So, they have kind of their own implication in the water, okay, and they also needs to be monitored. So, as we discussed that actually if we talk about water quality parameters, the list is quite extensive, it is not just limited to a few. So, there are much more water quality parameters, but these were the major ones which we discussed. So, we will conclude this lecture here, and in the next class then we will now focus on the treatment aspects. So, why we need treatment and what is the basic philosophy and approach of the treatment which is adopted for the municipal water supply systems. So, see you in the next class. Thank you for joining.